We usually think of light as traveling in a perfectly straight line, but its path is actually easily manipulated. When light strikes a smooth, polished surface, like a mirror, it bounces right back to our eyes. This is the simple reflection of light. But look at what happens when light passes from one transparent medium, like air, into another, like water. As the ray enters the new material, its traveling speed changes, which immediately alters its direction. This bending of light is called refraction, and it's why a pencil drops into water and suddenly appears broken in half. These bouncing and bending light rays create two distinct types of optical illusions. Real images are formed when light rays actually meet, meaning they are tangible enough to be projected directly onto a physical screen. Virtual images, on the other hand, are formed by the apparent intersection of light rays when extended backward. They exist only as a projection inside our minds, like the room you see behind your bathroom mirror. Every optical tool we use relies on these two behaviors. Understanding exactly how light reflects off surfaces or refracts through different materials is how we decode the mechanics of everything from the lenses in our own eyes to the mirrors on our cars. To understand curved or spherical mirrors, we start by imagining a complete sphere. By cutting a piece from that imaginary shape, we get two specific types of reflective surfaces. A concave mirror is a spherical mirror that curves inward, while a convex mirror has an outward curved reflective surface. We map these curves using strict geometric markers. The imaginary straight line running directly through the middle is the principal axis. The exact central point on the mirror's reflecting surface is the pole, and the dead center of that original imaginary sphere is the center of curvature. When parallel light rays strike a concave mirror, they all reflect and cross at a single specific spot on the principal axis. This point is the principal focus. Geometrically, the distance to the center of curvature is exactly twice the focal length, which gives us the equation r equals 2f. Because they reflect light predictably, dentists use concave mirrors to create enlarged images of your teeth. Convex mirrors curve outward to provide a wider field of view, making them perfect for vehicle rearview mirrors by consistently forming small, upright virtual images. When light completely crosses over from one transparent material, like air, into another, like glass, it doesn't just bend randomly. The change in direction follows a very strict mathematical ratio based on the speed of light in those specific materials. This diagram illustrates a principle known as Snell's law. It states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is always a constant value for any given pair of media. Spherical lenses use this exact bending principle to manipulate light. Convex lenses are thicker at the center and are designed to converge parallel incident light rays to a single focal point. If the lens is thinner at the center, it becomes a concave lens, which forces those parallel rays to spread out or diverge. This coordinate grid shows the sine convention, a strict set of Cartesian rules used to track these changing angles and distances. By placing the optical center of the lens at the origin, the 0 point on an XY grid, we can accurately assign positive and negative mathematical values to the distances of our objects and images. By combining the geometric coordinates of the sine convention with the constant ratios of Snell's law, predicting exactly where an image will form through a piece of glass is no longer a guessing game. It is precise, solvable mathematics. This math allows us to control magnification. Magnification is a metric, represented by the letter m, that provides a direct ratio comparing the physical height of an image produced by a lens to the actual height of the object being viewed. By altering the physical curvature of a lens, we change the distance at which the image forms. Manipulating this image distance directly manipulates the magnification ratio, turning a standard piece of transparent glass into a powerful magnifying tool. The ultimate measure of a lens's ability to forcefully bend these light rays, either converging them tightly or diverging them widely, is called the power of a lens. This diagram shows the formula for this capability. P equals 1 divided by f. In this equation, there's a critical rule. The focal length, f, must strictly be measured in meters. As that focal length shrinks, the power of the lens mathematically increases. The result of this equation is measured in diopters. A diopter is simply the standard unit of measurement for the optical power of a lens. If you wear glasses, That specific number written on your doctor's eyeglass prescription is exactly this measurement. Because of the sign convention we established earlier, converging convex lenses always have positive power, resulting in a positive diopter prescription. Diverging concave lenses spread light out and carry a negative power, giving them a negative diopter prescription. The next time you put on a pair of prescription glasses or check a rearview mirror, you are utilizing an intricate manipulation of physics. Our clear view of the modern world is entirely dictated by the precise mathematical bending and bouncing of light.